Hello everybody. So today we're going to start taking our discussion of energy, the ability to produce change, and its conservation, if there are no external forces, into a little deeper territory for AP Physics C mechanics. We're going to start that by expanding our idea of work a bit, okay, into some multi-dimensional vector algebra, as you will see here. So here's an example, one very much like we've done before. We've got a box here. It's being pulled by an applied force, which is at an angle theta. It's being pulled over a distance we will call d, and it's being pulled, just to make things easy, at a constant velocity. Okay? So, if we're going to look at this from an energy perspective, we need to define a system. And if our system is the box and the Earth, it's not isolated. You can clearly see the external applied force. Something's applying that, and whatever that something is not part of the system. Right? So that means there's work being done. Well, we have defined that work in the past for constant forces as external force times the distance times the cosine of the angle in between, FD cosine theta. And again, Fext is the external force, which in this case is the applied force. And theta, got to be careful what angle theta is. Theta is the angle between the external force and the displacement. What's the angle in between? Well, to see that, you have to draw the vectors tail to tail. Not head to tail, which is vector addition, but tail to tail. So, if this is our external applied force, the displacement in this diagram is horizontal to the right, so then this is the angle in between. Now in this case, that happens to be this angle in the diagram. It doesn't have to be that way, just the way it worked out in my example. Right? So if you're trying to figure out what theta is in this equation, remember that it is the angle in between the two vectors, the external force and the displacement, in which case you need to draw them tail to tail. Well, one thing I want you to notice here is that we are multiplying together two vector quantities, the external force and the displacement, but we're getting out a scalar quantity, an amount of work. This doesn't have a direction. This is just an amount of ability to produce change. Well, when you multiply two vectors and the result is a scalar, that's one of three kinds of vector multiplication. And it is known as the scalar product. Scalar product because you're getting a scalar out. And shorthand, because of the symbol we're going to use, is called the dot product. I've mentioned once or twice that there is actually three kinds of vector multiplication. There's the kind we mostly did last year, which is a vector multiplied by a scalar. Okay, like think of our kinematic equations, 1/2 at squared, where the acceleration is a vector, but t is just a scalar. Right? In which case you just get a vector out with the same direction as the original vector. It's just been modified in length by the scalar part. Right? And when we write that, we write it with parentheses. And this is our second type. Now, we were doing this, we did this last year, right? We did this version of work, but we didn't really talk about it this way because I didn't want to get into that much math, which we need to be able to get into 3 dimensions here, so we need to be able to do the vector algebra. The third type is something we won't see till we get to rotation, which is something called the vector product, which is when you multiply two vectors and you get another vector out. Right? So this is multiplying two vectors and getting a scalar. There are many different places this pops up in nature. This is the first one we've seen. Right? A scalar product is needed to completely define the work. So here's a little mathematical definition of what scalar product is. It's the magnitude of one vector, the size of one vector, times the scalar component of the other vector that's in the same direction as the first vector. Now, I'll explain to you what that means in a little bit, but suffice it to say that if we're using generic vectors A and B, we write it with that little raised dot, hence the name dot product. So A dotted with B is AB cosine theta. And you could read this as I just did as A dotted B, or A dot B, or you could say the scalar product of A and B, right? But that's why this is called a dot product. Okay, you could read it as A dot B, A dotted with B, right? Or just the scalar product of vectors A and B. Right? Notice how this is exactly how we defined work, right? But we derived this expression specific for work, right? But of course, it is actually a scalar product. Okay. So, using that definition, what does that really mean? Well, let's say we have these two vectors A and B, and I'm drawing them tail to tail so that we can see the angle in between, theta. According to our definition, right, the scalar product is the magnitude of one vector. So if we're going to do A dotted with B, it's the magnitude of one vector. So I'm going to just go in order here. So that's the magnitude of A, notice, which is just A with no arrow. The second part is the weird part. The scalar component of the second vector along the direction of the first. In other words, we need to figure out how much of vector B is in the same direction as vector A. To do that, we are going to break B up into perpendicular components, one component of which is along A, and the other component of which is perpendicular to A, because perpendicular things don't affect one another, right? They're independent. So, if there's a part of B that's along A, right? And there's a part of B that's perpendicular to A. See the little right angle then? Then this is the scalar component of the second vector along the direction of the first vector. This is how much, this red vector here, is how much of B is in the same direction of A. You with me? Breaking it up into perpendicular components, because this is the part of B that's not at all in the direction of A, which isn't important here, because that's not what the definition talks about. So how big is this vector? Well, we've got a right triangle, so right triangle trig. B is the hypotenuse. This side is the adjacent side to the angle theta. So this side would be the hypotenuse times the cosine of the angle. The hypotenuse is B, right? So B cosine theta. B cosine theta tells us how much of B is in the same direction as A, as long as theta is the angle in between. Plug that in, right? Because it's the magnitude of 1 times this one. And now we are left only with scalars on this side, and therefore we can do normal scalar algebra, right? Which means commutative associative properties hold. And we get AB cosine theta. This is how the definition leads us, all right, to the math model we've been using for a two-dimensional dot product. But what if we change the order? What if it was B dot A? B dotted with A. Does the order matter? In other words, is the scalar product commutative? Scalar product commutative. We know, for example, that vector addition is commutative. But is the dot product commutative? Well, using our definition, the magnitude of one vector, since our first vector is B, that would just be B, times the part of A that's in the same direction as B. So we got to break up A into perpendicular components. See that one? Right. This is the part of A that's perpendicular to B. And that is the part of A that's in the same direction as B. With me? This is the part of A, so I'm breaking this vector A up into perpendicular components. Here's the part of A that's perpendicular to B. Here's the part of A that's parallel to B, or in the same direction as B. And notice, in this little right triangle, A is the hypotenuse. Here's the angle, adjacent side, so it is hypotenuse cosine of the angle, or A cosine theta. Plug it in, and again, we are left only with scalars on the right-hand side, which means we can rearrange them at will, and we get AB cosine theta. the magnitude of A times the magnitude of B times the cosine of the angle in between, which is exactly the same thing that we got before, which means scalar product is in fact commutative, which is just a nice thing to know so that order isn't really important. Really doesn't matter in our work equation whether it's FD cosine theta or DF cosine theta. Why then do we tend to write it as FD cosine theta? Well, because force is in newtons, displacement is in meters, and a newton meter is a joule, and so it's just in order that way. But it really doesn't matter. So you see scalar products in the future, not in this class, but in other classes, whether it's physics or high-end math, and you'll end up knowing that it is commutative. So let's do a little example here. Here we have a constant force given in our old friend unit vector notation as 2.0 newtons I cap plus 4.0 newtons J cap, and it's pulling on a box which moves the box through a two-dimensional displacement of 3.0 meters I cap minus 5.0 meters J cap, right? This is the position vector, a multi-dimensional position vector instead of using an X, a Y, or a Z for one dimension. And so delta R is the change in position or displacement. And I want to know how much work is done by this force. Right? Now, it's a constant force, so just like the ones we've been doing, but this is basically a two-dimensional problem, right, in unit vector notation. Now, I'm going to actually have you do on the follow-up worksheet to this a three-dimensional problem, but and I'm going to have you do that and kind of prove something, but we'll get to that after we work through a little simpler example here. So let's do this problem two different ways. Okay? In both cases, we're going to use our equation that work is F dot D, the force dotted with the displacement, the scalar product of force and displacement, however you want to say that. So first we're going to grind through our basic definition, which is that work is FD cosine theta. It's the external force times the displacement times the cosine of the angle in between. But in this case, we don't know exactly how big the force is. We don't know the magnitude of the force. We don't know the magnitude of the displacement, and we certainly don't know the angle in between them, but we're given enough information to figure that out if we draw out some diagrams and then do some right triangle trig. So let's draw out a vector diagram to represent the force vector. It has an x component of 2.0 newtons I cap. Remember, I cap is horizontal, and it's positive, so we'll go to the right 2.0 newtons. J cap is vertical, and positive means up, and since it's addition, we'll go head to tail. And of course, my diagrams are internally consistent scaling-wise, so notice that my 4.0 newtons is twice as long as my 2.0 newtons. And therefore, my two-dimensional force vector goes from the tail of the first to the head of the last. And I'm going to call this angle here down here at the tail that we need in order to describe the force vector. I'm calling this alpha because I don't want to confuse it with the theta in this equation, right? Theta is the angle between F and D at this point. So this is just the angle alpha. Everybody okay with that? So we're writing out the vector F, the force vector, if you will. All right, and drawing out the diagram from our unit vector notation. Well, hopefully at this point you're like, okay, I can figure out what F is now, right? It's a right angle, so we can do a little Pythagorean theorem. I'm going to keep an extra sig fig here and round off at the end. So this is 4.47 newtons. To find this angle, we'll do an inverse tangent, opposite over adjacent. Make sure your calculator is in degrees. Again, keep an extra sig fig. And we get 63.4 degrees. So this force vector is actually 4.47 newtons at 63.4 degrees using counterclockwise from zero notation. If I had given that to you at the beginning, we wouldn't have had to do this part, but then we wouldn't have had unit vector notation. Well, what about the displacement? Where does this box move? Well, we can write out a diagram to represent this displacement vector. 3.0 meters I cap would be again to the right, but minus or plus a negative 5.0 meters J cap would be down. Right? So plus a -5 is down. Right? These aren't, though I'm using the same scale, it doesn't really matter, these two diagrams, but just internally within the diagram. And therefore my displacement is actually here, from where I started to where I ended, right? From the tail of the first to the head of the last. I'm calling this angle phi, P-H-I, right, phi, to again distinguish it from theta and alpha, different angle. But the same math now, we can find the magnitude of the displacement by doing a Pythagorean theorem. Keep an extra sig fig, 5.83 meters. We can find the angle phi to give us the angle of our displacement by taking an inverse tangent of opposite over adjacent, which gives us 59.0 degrees. So, I can now use this equation. I know the magnitude of the force, 4.47 newtons. I know the magnitude of the displacement, 5.83 meters, but I still need to know theta, which is not alpha or phi. It's the angle in between the force and the displacement. So let's figure that out by drawing those two vectors tail to tail. There's the force, there's the displacement. Can we figure out the angle in between? We sure can. Right? We know that one's 63.4 and that one's 59.0. So the angle in between is that angle, which is just 122.4 degrees. Plugging all three of these in there, we get a work of -14 joules. Remember that in terms of work, that means that you are transferring 14 joules of energy out of the system. Maybe this box is already moving and you're slowing it down, right? So that there's a decrease in the kinetic energy of the system, say. Right? But you're doing negative work in this case, which is not a directional thing. Right? It's whether you're transferring energy in or out. So in this case, you're transferring energy out of the system. Now, this took a lot of work to figure out this work. I know, there's just not another word. We had to draw the two diagrams. We had to figure out all the angles and the magnitudes and, doing this. And certainly this would work. But if we apply what we know about dot products now, scalar products, we can actually do this quicker, right, if we do the vector algebra. So here's method 2. In this case, we're going to plug in our force vector and our displacement vector in unit vector notation, and then we're going to do the dot product. Well, this is multiplication, right? So just like in regular algebra, we're going to dot product these two binomials, which means we're going to do a little FOIL-ish thing here. And in the end, we'll end up with 4 terms. Right? We're going to take I'm going to get rid of the units here for now, right? But note that we're always doing a Newton times a meter. Hint, hint. So we're going to take this term dotted with this term, and then this term dotted with that term, and don't lose the minus sign, and then this one dotted with that one, and then this one dotted with that one. When I have you do the three-dimensional example, right, on your worksheet, you'll get 9 terms, as you will dot product 2 trinomials, right, will give you 9 terms. Now, how to do each one of these? Well, they're dot products, but the 2 and the 3 are just scalars here, so the coefficients we can just pull, right, outside, and that leaves us with this, 2 times 3 I cap dotted with I cap, minus 2 times 5 I cap dotted with j cap, plus 4 times 3 j cap dotted with I cap, minus 4 times 5 j cap dotted with j cap. Now, certainly we can do the multiplication of the scalars out in front. That's just scalar multiplication. You've known that since elementary school. But how do we do I dotted with I and I dotted with j and so on? Well, we apply our definition of dot product, which is the magnitude of one vector times the magnitude of the other vector times the cosine of the angle in between. Well, remember that I, j, and in your worksheet, k cap are all unit vectors. And unit vectors have a magnitude of 1. That's why they're called a unit vector. They have a magnitude of 1 unit. So really all we need to know is the angle in between. Well, let's check out I dotted with I and J dotted with J. What's the direction, or sorry, the angle in between I and I, since they're the same vector? Not trying to be tricky here, right? The angle in between is 0. And what's the cosine of 0? It's 1. So I dotted with I and J dotted with J are 1 times the cosine of 0, which is 1. And so I dotted with I and J dotted with J is 1. That's all it is. It's a scalar of 1. On the other hand, J dotted with I and I dotted with J, well, what are the angles between I and J? Or if we had a K, I and K, or J and K? Well, those are all perpendicular components, and therefore their angle in between is 90 degrees. And the cosine of 90 is, of course, 0. There is no part of horizontal that is vertical, and there is no part of vertical that is horizontal. Right? So cosine of 90 is 0. So I dotted with J and J dotted with I is 1 times the cosine of 90, which is 0, or 0. So these two cancel out right away. Any vectors which are perpendicular to one another have a 0 scalar product, right? Because there are no parts of them that are in the same direction. They are completely independent of one another. Scalar product is really a measure, in mathematical terms, is really a measure, geometric terms, I suppose, is really a measure of how parallel two vectors are. Right? The more parallel they are, the bigger the scalar product is. Right? In terms of our energy idea, the more that you're pulling in the direction the object is moving, right, the more of your pull is actually helping the object move and transferring energy. So this leaves us with 2 times 3, because I dotted with I is 1, minus 4 times 5, because J dotted with J is 1, and Newton meters, I put in the units again. A Newton meter is, of course, a joule. So this is 6 joules minus 20 joules, or negative 14 joules, and you are done. Now, I know this seemed to take a little longer, right? But that's because we had to talk about how to do dot products of unit vector notation. But once you've seen this and done it a few times, especially once you go through and kind of derive a symbolic three-dimensional dot product, as you will on the worksheet, right, you'll see that there's kind of a pattern they follow, right? An equation that's not that hard to memorize. It's not on your equation sheet, but it's certainly, if you put it in your calculator or you memorize it, is something you could use on an AP test, right, which allow you to do scalar products written in unit vector notation fairly easily. Okay, you can, not mess at all with the thing and just know, right? Again, the ones that are parallel, right, actually stay there. Right? The rest of them, all the perpendicular ones, are zeros, right, and cancel out. Questions? Okay. There's a little primer on taking work now into multi-dimensions using unit vector notation. Have fun with that proof.